So we would like to discuss the notion of separability in Banach spaces. And pretty much the idea is quite simple. So a Banach space X is called separable if it contains a countable dense set. So dense, or everywhere dense if we like, means that it has non-empty intersection with an open ball, with every open ball. And countable, in fact, we're only interested in non-trivial Banach spaces. So in this case, countable will mean infinite. Countable means that it is in one-to-one correspondence with n. So simply speaking, we say that it's dense if you can find a sequence so that the smallest closed set that contains that sequence is the full Banach space. So equivalently, this means that there exists a sequence in X, let's call it Xn, and in Z, that meets, intersects, if you like, every open ball. Okay, or equivalently, and this is a very nice equivalence to know, or equivalently, so this last equivalence goes to meets every open ball, the least, the smallest closed set that contains it is all of X. Okay, we have a very nice theorem here. We're not going to prove this. It's not hard to prove it, but we're not going to prove it. That says that if the dual of a vector space of a Banach space is separable, then X is separable. There's also another really beautiful theorem. It's not easy to prove, but it says that if you take all separable Banach, or that any two separable Banach spaces, any two infinite dimensional separable Banach spaces are pretty much homeomorphic. This means that there is a continuous map which is one-to-one and onto, and whose inverse is also continuous. So as metric spaces, they're pretty close to each other, in other words. They're not isometric, but they're very close to each other. So in any case, I think we should bypass this for the moment being and just give some examples and try to understand out of the spaces that we have seen so far, which ones are separable and which ones are non-separable. And pretty much the answer is every single thing we have seen is separable with the exception of L infinity. So L infinity is not separable. And here in this discussion, I'm not including the fancy LP spaces for measures that we have seen. Those can be quite wild if the measure is wild. But in terms of, let's put them down concretely. So LP, C naught, C, C of K for a compact metric space. All of these are separable. Okay. And it might be a good idea to give an idea of what and L1 I should put. So for example, let's give an example of what would be a countable dense set in L1. Okay, I think this would be a nice example. So what we can take here is all x's in L1. So let's call this D, x in L1, so that they're eventually zero. And all of their terms are rational numbers. So, so what do I mean by this? So take a sequence that looks like this, 1, 2, and then 0, 0, 0. In general, if you take a sequence which is eventually 0, there's no doubt about it that it's an element of L1 because the sum of its absolute values is a finite sum. So we take all such sequences, and in particular, we try to make sure that all the entries, of course, 0 is a rational number, but the non-zero entries are also rational numbers. It turns out that the set of such sequences is a countable set, and also it turns out that it's a dense set. So that's how we find a dense set in L1. The same description that we gave here pretty much works for each of the spaces, LP, C naught, and C. This set that was just described is a subset of is a dense subset in also those spaces. Now, it would be kind of interesting to ask why isn't L infinity not separable? So how about L infinity? And what you need to do is take the following sequences that consist of ones and zeros. So if we take the subset U, which is all xn's n in Z, with xn equals 0 or 1, all of them, then it turns out that this is an uncountable set because it has as many elements as the subsets of n. So it's uncountable, and the distances between any two things in x and in U is 1. Okay, because if you take two distinct elements, then they will be different at least one coordinate, and so the absolute values of their differences will be 1 at least one point. So if you think about it, having an uncountable set that has so much distance from each other does not allow does not allow the space to be separable, for the very simple reason that because of this you can have balls, open balls, uncountably many, that have no common points with each other. So you just have too many of these balls. So if you had countable dense set, then it should have at least one element in each ball. But that means that you should need at least uncountably many elements to be present in all these balls that have that have empty intersection with each other. So something like that, of course, tells you that L infinity can never be separable. And that's how this is shown. Okay, and that's all. Thanks for watching.